Hello, everybody. We are in section 2.1 still, and now we are going to look at our ideas of average rate of change and instantaneous rate of change in a more geometric way. And that is going to be using the idea of secant lines and tangent lines. So here are our definitions. A secant line, or a secant to a curve, is a line that joins 2 points, P and Q, on the curve. Okay, so we can sketch this out here. Let's give ourselves a little curve of some sort, and we're going to put 2 points on there. This is P and this is Q, for instance. And the secant is the line that goes between those 2 points, just like this. So that is a secant line. Now, a secant line can cut through a curve more than just at those 2 points. Let's see, let's draw a little curvier curve. Okay, we could say here is point P, and over here is point Q. We can still have a secant line between those 2 points. It's just the line that's going to join those together. Boop, like so. Okay, so that's a secant line for that curve between those 2 points. And what we're looking at here is actually going to relate to the average rate of change of that function. We'll see how that ties in a little bit later. All right, so a secant line joins 2 points. Fun fact, the word secant comes from the Latin secare, which means to cut. And so you'll see how those lines cut across the curve. That's a delightful fun fact that I learned from a former student of mine who is a botanist now, and so he knows a lot of Latin. I thought that was pretty cool. So those are secant lines, yeah. Now that's in contrast here to a tangent line. A tangent to a curve is just at a single point P. And the Latin for this one, tangent, comes from the Latin word tangere, which means to touch. And so this is just going to touch the curve at a single point. We'll call that point P. And the tangent is defined as being the limiting case of all the secants PQ as Q approaches P. Now that's kind of a bit of a wordy definition there. So let's put some pictures to this. Let's draw a little curve with a secant like we did before. Okay, P and Q. There is a secant, line PQ, like it says right here. Now we want to let that point Q approach P. So Q here is going to shift along our function until it gets closer and closer to P. So Q is going to approach P like that. So let's let it approach a little bit and see what happens. All right, I'll try and make my curve look similar. Here's point P still. And Q has made a little approach here. Let's say point Q has now moved up to the top of the curve there. All right. There is another secant line, PQ. All right. Let's let Q do a little more approaching. Get a little closer. All right, there's point P hanging out still. And let's say point Q has shifted down so it's over here now, approaching P, definitely. We've still got ourselves a little secant line that runs just right along the edge of that curve. We can't really see how it's cutting through the curve very much at this stage, but we've still got a secant line. Now, in order to get ourselves a tangent line, we have this idea of it being the limiting case. And so the ultimate closeness that can exist between these 2 points, P and Q, as Q is approaching P, the ultimate closeness, or the limiting case of closeness between those 2 points, would be where they're actually sitting right on top of each other. If Q approaches P so much that Q and P end up in the same place, that's where we're going to have a tangent line. And then it's going to look like this. Okay, there was point P, and Q approached so much that point Q is now directly on top of point P. So we have point P and point Q sitting right there in the same point. In fact, at this stage, we really just consider this to be this single point P, since P was there the whole time. So Q, get out of there, little buddy. And now our line looks like this. The 2 points have come together. This is the limiting case of all those secants. And this is now a tangent line. Okay. So that tangent line just touches the curve very lightly at that one single point right there. Okay. Comes in and touches. That's our limiting case of all the secants. All right. Now, for a little demonstration that might be a bit better than my hand-drawn pictures, I'd like to take us over to the website Opengraphingcalculator Com. This is a graphing website that's pretty similar to Desmos, if you've ever used that one. I think Desmos can do a fairly similar thing, but I'm going to rep this website here because my former computer science professor actually made this from the community college I went to. So yeah, representing Mr. Redden today. All right, so here's opengraphingcalculator.com. And I'm just going to type in some little function for us. I'm going to say y equals -1/5, and then my keyboard does not want to cooperate. -1/5 x squared. There we go, x squared, and then plus 4x. That is easier to type in when you're not doing a touch screen, FYI. All right, and let me zoom out a little bit so we can see our curve. Okay, so this is kind of a little parabolic shape like the pictures we were just looking at on the hand-drawn notes. And now I'm going to add a couple points to this curve. We add points by clicking this button right here. And it's going to call that first point A by default. That's okay. That was like our point P in the notes. We just need 2 points, pretty much regardless of what they're called. Okay, so we'll call those little guys A and B instead of P and Q. All right. Now we are going to add another graph because we'd like to create a secant line between those 2 points. So it's pretty easy on here. You just type in line A, B, and it puts a line between points A and B. All right. Now we can see our secant line there cutting through the graph. Okay. And if we want to consider what this looks like as a tangent line, we need to see what happens if we allow B to approach A and see the limiting case of what happens to the secants there. Okay, now when I hover on that graph, it does kind of get a little faded looking, but bear with me. Let's let B approach A. Notice how it's adjusting the secant line for us. So that's kind of like the second hand-drawn picture there, where B has approached a little bit. Let's let it approach a little more. All right. Yeah, it's getting closer and closer there. We can barely see, but you can still see how this is a secant line, especially if we zoom in, how it is still cutting through the curve. All right, we're gonna let B approach A a little more. Still a secant, believe it or not. Zoom in, oh, there's the difference. All right, and so now we let B approach A until we hit the limiting case of those 2 points being directly on top of each other. So B and A merge together. And now this is a tangent line, the limiting case of the secants. Ultimate closeness between our 2 points leaves us with really just a single point on the curve where that line touches. And so we've got our tangent line. All right, so that's the difference between secant lines and tangent lines. In the next video, we'll see what's going on with the slope of these lines and how that relates back to our rates of change.